Hello everyone. We'll begin with this new fresh chapter called the Stress Strain Temperature Relations, and it's chapter 5 in your textbook. So, just to summarize what all we have done until now, we have in the last chapter we have studied the ideas of stress and strain at a point. Okay, so we have studied about the stress and strain at a point. Okay. Now this at the point is very important because the point O for us, if you remember in most of the diagrams, was that point where we had defined what stress is and where we had defined what strain is. So the way we had done was, as you have seen, was completely different. This was done using geometry, and this was essentially done with the force equilibrium. Okay. And then there were about the continuity of displacements and things like that, but the methods were completely sort of independent. The theory was independent. What we did not do in the last chapter was that we never specified the nature of the material of the body. I mean, the theory which we had learned for stress, the theory which we had learned for strain, that would be true for any material. I mean, say plastic, say iron, say a chalk, bone, wood, rock, anything. So we did not specify the nature of that material, and that is something which we want to address right now, and we'll try to motivate why we would want to do that. Now you have three equations of equilibrium. Okay, then can you recall them, what the three equations of equilibrium were this at this time? You had six components of stress. Okay, there were in reality 9, but we had shown that the shear ones were equal, so you ended up with 6 components of stress. Okay, and then you had 3 components of displacement. Okay, and whatever u, v, and w, right, for the displacement vector. And then you again had 6 relations of strain. Okay, so the strain displacement relations were 6 of them. You know all those components, and again, because they were in total 9, but because of the symmetry of the stress, the shear terms, you would have in the okay, fine, you would have only 6 of them. Now you should by this time be able to tell what are the 3 equations of equilibrium. Okay, and what are the 3 components of displacement? Well, that answer is definitely there. What are the 6 components of stress and how they are related to the forces? By this time you should be able to quickly go through all those things, and then how the 6 relations of strain are related to the displacements. Okay, this is something which you should be able to tell right now. Okay, so this essentially is 3 equations of equilibrium is like one each in the direction. Okay, so in the x direction one equation, in the y direction and the z direction one equation. So we have 3 equations of equilibrium, but definitely go and check back in the theory to ensure that. So what this tells you, you need more relations to solve, say, the stress Ij and strain Ij. So this, you remember what the index notation was: sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 2, 2 3, and so on. So I and j can each take a value of 1 or 2 or 3. So there are a possible of 9 combinations in total. So that's how I will write this sigma ij in eij now. So this one symbol means that all the 9 components can be written using this. So it is very clear that I and j will both have values going from 1 to 3. Okay, so you need more relations. I mean, because you see there are only 3 equilibrium equations. You have to find 6 stress components. There are 3 components of displacement, and you have what 6 relations of strain to find out. Okay, so it seems, I mean, you have lots to find and less information available. So you have 6 things known and somehow 12 things are to be found out. Okay, so you want to find, say, the stress and strain in a body, meaning at any point in this solid body you want to find the stress and the strain, and you will need some more information for this. So in this chapter, we will concern ourselves with the relations between stress and strain. So what is the relationship between stress and strain is what we will concern us. Now, there are 2 methods with which you can, so I'm going through the introduction of this chapter in your textbook, okay? So there are 2 approaches which we can use. One is the relation based on experimental evidence. Experimental evidence at atomic level. And the second method, I mean, how to find the stress and strain, that's what we are going to do. What is the relationship between stress and strain? So one relation can be experimentally found out at the atomic level, and the other method is to this relation which is experimentally found out at macroscopic scale. So macroscopic scale is the scale which we are seeing with our naked eye, this continuum solid scale which we have assumed. Okay, so that is what these 2 approaches are, and you can like go to any point, and what should be the relationship between stress and strain at that point. That these are the 2 methods, that you go to the atomic level and then do some experiments and find out, or look at it as a continuum and then do some experiments and find out. Similarly, now move to the next place and repeat the same exercise over there. So there are 2 methods over there. So the first method, though looks very exciting at first, this has not actually developed until now to a point that we can teach it to, say, the second year undergraduate students. In the sense, it's still an emerging area. Okay, a very new technology, and some of the PhD students at IIT Delhi are working on this. I mean, what is the relationship between stress and strain at the atomic level? So they conduct these simulations. Some of them try to do it through some indirect experiments, other ways, and then they try to find out these sort of things. So this is something which we want to ignore for this course. Instead, we'll focus on something which is more widely known, and hence, because it's more widely known, then you are expected as a student to know this. Okay, so we'll be focusing on the continuum scale, and we'll try to get this experimental data at the macroscopic level to be able to find the relationship between stress and strain. And you would do that using some physical and mathematical arguments as we move along. Okay, So that's the sort of motivation in trying to study this subject. Okay. Okay, so let me just rub this off. So there is a lot of talking in today's and many other classes. So there's less of maths, so to say. I mean, at least in the initial parts of this chapter. Okay, so when you want to describe the stress strain behavior of a wide variety of materials like metal, wood, polymers, composites, and so on, we want to basically distinguish between certain materials, and for that we need some sort of an experiment to be done, and you can do that while sitting at your homes, I mean away from the classroom. It's easy to do. Okay, let's see how does that happen. So what you have to do is we want to, I mean, forget about the stress strain, we just want to study about the load deformation behavior. Okay, as of now, just to get started with this subject, and as we study we'll be discussing stress and strains. So what you do is you straighten a paper clip, straighten it with your hands, okay, and then clamp it between a book and the edge of a table, something like this. Okay, so this is your straightened paper clip, and we are not telling you to do it with a needle or some other thing like that, just because this does not have any sharp edges, so it's safe to do all these things. Okay, so please get hold of a paper clip and put it like this between the book and the edge of the table. So this is the edge of your table, and that's how you do it. So this is clamped in the sense this is fixed, so this is a clamp one. You have fixed it with a heavy book, and what you do now is you press on it lightly, okay, at the edge. Lightly is an important word, okay, as light as you can be, okay, and still be observing some deformation. So you press it on lightly and release the load, and you will notice that it returns to its original shape. So if this was like this, after the application of load, perhaps small load, it will change like this, and as soon as you remove the load, it will come back to this exact position as well. Okay, so it comes to its original shape. This illustrates something called the elastic deformation. Okay, so all these terms are very important. In your textbook you have these terms written in italics. Okay, so please read them. And elastic deformation means that it is a deformation which disappears on the release of load. So you have seen that, you should have done this experiment by now, and you should have seen that. So as soon as you release the load, the deformation is gone. Okay, so that is what an elastic deformation is. Now let's conduct another experiment. In this case, you again load this wire, and note that the greater deformation requires a greater load. Now you apply, say, a force of magnitude 10 units, and it will deform like this. Magnitude force, if you apply a greater force now, after releasing it again, okay, after removing the force and letting it come back, you now apply a force of, say, 20 or 50 units. This will deform more. Okay, so this is an observation you can make. Don't apply a lot of force, but at the same time apply more than what you had applied before. So you will see that the uh, greater deformation will require a greater load. Now you keep on increasing your load, and eventually you will see that the deformation keeps on increases. This is something which you should observe. I mean, you can take one value, release it, let it come back, take second value, release it, come back, and so on, and you will see that the deformation is increasing each time. So now the release the wire. So there will be a point when you keep on increasing that the wire will not come back to its original. Say you apply a force of 100, just as an example, it's much higher than what you had applied, which was 10. Now what will happen is maybe it has deformed like this. Sorry, maybe it has deformed like this. Now once you remove it, then it will not actually come back to this place. It will come to something like this. And this is what is meant by this. Okay, increase the load and note that finally a value of the load is reached such that when this load is released, the wire does not return all the way to its original shape but remains partly bent. Okay, so that is an observation which you should be able to make. So this is no longer a elastic deformation, because clearly how did we define elastic deformation? That the deformation should disappear as a load is released, but clearly now the deformation is not disappeared. I mean, there is some deformation which is there even after the removal of load. Okay, now hang on the end of the wire a fixed load large enough to cause a permanent bending, and note that the amount of deformation does not increase with time. So this is what you must do. On this originally straight wire, hang a weight. Okay, maybe you can get hold of a string and some slightly heavier thing around you, and it should be such that when it changes its shape after you apply this load, maybe it will become like this, maybe it will become like this. Okay, now what you will see is that the weight keeps on hanging. Okay, but the deformation does not increase. So the amount of deformation does not increase with time. Okay, so there will be a stage, I mean it will just keep on holding. So time will pass, but this is where this deformed configuration will lie. This is called a plastic deformation. So how is it defined? It is defined, this is the second part, and again it's in the italics. It is defined as a deformation which depends on load, clearly, right? The more load you apply, the more deformation happens. So it depends on the load. Okay, and other than that, it is independent of time. Okay, and the most important part, remains on release of load. Okay, so the first characteristic which depends on load is shared by elastic deformation as well. Even in the elastic case, you apply a little load, it will deform. You apply a little more load, it will deform more. Okay, but the plastic deformation, other than having this property, I mean, if you take a bigger W, say W plus say 2W, then it will deform more. Okay, but the difference here would be that this deformation will not depend on time. I mean, if once it is done, it is fixed. And lastly, it will remain on the release of the load. The deformation will not go away as it did in the elastic deformation. So you should be very careful of what a elastic and a plastic deformation is. Okay, now you have to do another experiment, and I'll just rub this part off. So why I insist you should try to do an experiment like this or similar to this, because anyone who teaches this subject to you, okay, they would have already felt what it means to see or visualize an elastic deformation and a plastic deformation. And I mean, for them, it is not just something which is being told to them, it is something which they may have seen several times. And you are learning this, and hence it is important for you to visualize it the way we are discussing. Like the deformation does not change with time. You have to really apply a very small load and keep on increasing it to a level that you see that there is no further change in deformation with time. Anyways, so what we do next is we bend the wire further and keep the force perpendicular to the wire. So the force must always be perpendicular to the wire. The force required to bend the wire 90 degree is greater than that required to initiate plastic deformation. So you had something like this. You want to now hold it at one point and bend it in this form so that this is perpendicular. So you will eventually get something like this. In your workshop, I don't know if you have done something called a pipe bending experiment. Okay, but it's a similar concept. So the wire, so you bend it, and what you notice is that the force which will be required to create this 90-degree bend is greater than what will be required for plastic deformation. Okay, and this is something which you can easily observe. I mean, you don't have to bend it all the way over here to do it, but you will see that for 90 degrees bending you require a much larger force compared to the plastic deformation. This increase in the load required for further plastic deformation is called strain hardening. Again, a word in italics. Okay, so let's say this is your initial undeformed wire. Apply a small load. Okay, it will be an elastic deformation. Apply a large load. Okay, it will be a plastic deformation, meaning it would have bent something like this. Okay, now you continue apply a larger force, only then you will achieve something like this. So the force which will be required over here, this may be 10, this may be just an approximation, say 50, and this may be 100. So this force to cause a 90-degree bend is much greater than what is required, or at least greater than what is required to cause a plastic deformation. Okay, so this phenomena is called strain hardening, and what you must note at this point is that as the load increases, the elastic deformation continues to increase, as is shown by the increased spring back upon release of the force. Okay, that is something you have already done. I mean, you keep on increasing and the deformation will increase and it will spring back to its original shape. Now, what you have to do is try to break the wire by bending it sharply. Okay, so you have done this. You have bent it. I mean, this was all a bending experiment. I hope you can see. And remember the cantilever beam which you had done. I mean, this is a similar sort of a cantilevered clamped arrangement in which this edge is fixed inside the wall which you have artificially created. Now you want to break the wire by bending. It will not be possible. Meaning you cannot like apply more force and break this wire. You cannot continue applying more force and break the wire. That will not happen. Okay, that's one important observation to take. No matter how much force you apply in this bending direction in something like this, you will not be able to break it. Break means in the sense not break it into two. This is where the fourth term comes in, which is called a ductile material or a structure. Okay, this is a structure, again a word in italics, for which the plastic deformation before fracture is much larger than the elastic deformation. So the plastic deformation before fracture is much larger than elastic deformation, and you have seen an example of it by the experiment which you should be doing. So I mean, it will deform a lot plastically before it actually fractures. So that's a long way to actually fracture it like that. And this is a ductile material. Okay, now you want to really get an understanding of what ductility is, and you will learn about how to quantify ductility in say your material science course. Okay, there they would teach you how you can quantify ductility of a material, like give a number that this is more ductile than this is a number for that ductility. So perhaps that you should learn in your material science course. It's a simple one word formula. Okay, so what we do now is, with this paper clip and perhaps a new one if you have already destroyed it by now, you would want to bend it into a shape of U. Okay, so let me just okay, so we want to bend it in a U shape. Okay, so any wire can be bent into a U shape. Okay, there's nothing incredibly hard about that. And you want to twist it as shown in figure 5.2. So once you get it of a U shape, or actually the shape should be like this, U shaped. Okay, and now you want to bend it like this. Okay, so you want to twist it is the exact word. So I think you can visualize how this has come up over here. Okay, so one part of it remains where it is, the other part has to be twisted. So you have to apply a rotation in this particular form, and this would be a twisting. Okay, uh, the plastic deformation up to fracture may be 100 times the elastic deformation. Finally, note the wire can be broken by repeated bending back and forth. Okay, so you have to do this several times to fracture it. So do this several times, I mean back and forth, to actually fracture this into two. Okay, this I mean it takes so much of effort to actually break it. Back and forth you have to apply this action which is shown in this twisting experiment figure 5.2 and get this done. Now the plastic deformation, finally note that the wire can be broken by repeated bending back and forth. This repeated fracture under repeated, this progressive fracture under repeated loading is termed as fatigue. This is again an italized word. So if you apply a load, and you can also do this like this. Take this wire and try to bend it. Okay, unbend it, bend it, okay, so on. So you will keep on doing it, and you will start notice that at certain point it will become weak and then break off from there. So that is what is called a fatigue. Okay, so these are the simple experiments which you can do to understand these terms. They have a much grander meaning when we will learn about solid mechanics and apply these concepts, but as of now you can just uh, get an idea of what these terms mean in the most crude and simplistic ways. Okay, now we repeat the bending experiment with a piece of lead from a mechanical pencil. Okay, so what we now do, so repeat the bending experiment with a lead from a pencil. Now if you do not have this, you can do this experiment with many things. And one is a piece of wood straw from your broom. Okay, you can do this with a matchstick. You can do it with even a lead from those automated pens. I mean, I don't know what they are called, the ones which in which you fill the leads. Okay, not like the uh, mechanical pencils. So any, just about anything. I mean, a matchstick might be something which is easier to find out, and you try to please do this experiment with a matchstick, and then you will see that it will have little deformation before fracture. So the earlier one, which was a ductile material, the metal wire, that would deform little in elastic, deform a lot in plastic before it actually goes to fracture. This one, on the other hand, it will show very little deformation before it fractures. Okay, such a behavior is called brittle. Okay, and there are many materials around you which you can classify. For ductiles, I think metals are the easiest cases for you to think of. Okay, then plastics are also, I mean, if it's a softer plastic, that is also a case of that kind. Brittle, on the other hand, something like a chalk or a rock, or this wood, wood is also an example of brittle. So you have bone, for example. I mean, you may have heard that, or you may have experienced a bone fracture at some point in your life. Materials like a bone do not allow a lot of deformation before they fracture. They'll have little deformation and they'll fracture. That's it. So that's easier. It's easier to break them deformation wise. And metal, on the other hand, as I have said, it requires a lot of deformation in the plastic deformation, which is it will not come back to its original shape. and before it fractures. Now, one other point which must be made over here, that this behavior of a brittle or ductile does not depend on the material itself but on the temperatures as well. There may be a material which is, say, ductile at room temperature, okay, but brittle at very low temperatures. Meaning, at very low temperatures, if you conduct this test, very low in the sense, for some of the steels it is like minus 60, minus 80, minus 100 degrees Celsius. You conduct those experiments in those low sub-zero temperatures, it will not show a ductile behavior. It will be like a brittle material. So it will fracture only after a little deformation. Okay. So this is something which you should know, so that it is not the material which is ductile or brittle, but also the conditions which help us distinguish between a ductile or a brittle material. And one example is given in your textbook, which we have just discussed. So just for the sake of being clear, I mean, if nothing is specified, we want to assume that it's room temperature. Okay, so no thrills at all about this. Okay, now there is another point which must be made, that the ductility will depend on the size of the structure. Okay, so this is something which I think may be better told to you in your course in material science, because then you can understand about the grains and the grain size and how ductility is related. And then there is something called the Hall patch effect. Okay, so I think by this time or maybe later you should have learned about this, and it is better we keep that discussion for that course rather than discuss it over here. Okay, so we won't be discussing this and some other parts related to it. Instead, we'll come back to uh, this so-called last part of this initial discussion. Okay, so please read this over there. I think it is much detailed and you will get a much better idea if you read this about ductility in your material science course. Okay, and it does not hamper in whatever we want to do in this course, so don't worry too much about it. Okay, another important behavior of materials becomes evident at absolute temperatures which are about half the melting point of the material. So if you have Tm as the melting point, and if you take half of it, and these are absolute temperatures, okay, and the absolute scale, the deformation due to the load, okay, will increase with time. Well, you can say the deformation with load has to increase with time. Well, the trick is over here with a constant load, meaning you take this material, okay, and I mean this thing over there, and you apply a load on it which is constant. Don't increase this, and then you will see that the deformation will keep on increasing as time passes for this constant. Remember, in the elastic case you will have to keep on increasing this load for it to get to a larger deformation. In this case, your deformation, the force remains the same, but the deformation is still increasing with time. This will happen if you do it at a very high temperature, this test at a very high temperature. Okay, this is indicated by this Tm by 2, the melting temperature by 2. Okay, and for steel normally this is around 480 degrees Celsius. this Tm by 2, and for aluminum the author says it is around 200 degrees Celsius. So this is what will happen. This is called creep. Okay, the deformation will increase with time despite having a constant load. You are not increasing the load, but the deformation keeps on increasing. So this happens. The application of this, yes, a lot. Anywhere where you have very high temperatures like a furnace or things like that, you will start to experience creep. So over time, and by this time it does not necessarily mean in terms of seconds. Okay, sometimes it is over days, weeks, months as well. But the point is that the force remains the same and still the deformation is keeps on increasing. So it's not a good thing to happen. Okay, now let's come back to okay, almost done. Okay, now another time dependent phenomena. Remember, plasticity was not time dependent. Do you recall that? We just did that. I mean, creep is clearly time dependent. Plasticity, one of the three tenets was that it is the deformation does not depend on time. So keep all this in mind very carefully. Okay, and you may have to look out for these words in YouTube, as I have said before. You should do that so that you get a physical picture about it, and they will prove to be immensely helpful in trying to learn the concepts which we are doing in this course. So if you are not doing it, please pause the video right away and do that. Okay, so moving ahead, we have another time dependent phenomena, and it is the slow recovery of shape when some materials undergo when they are unloaded. This may be observed by folding a piece of paper. All of you can do that, and you should do that. Piece of paper, and then releasing it. As soon as you release it, you will notice that there is first an immediate elastic spring back, followed by a relatively slow unfolding. Now it will not unfold back to the original paper, but that process will be there, that there will be a first immediate spring back uh, uh, recovery, and then it will start to gradually slowly unfold. You should see that. If you are in doubt, you can definitely do it over and over again until you are able to see this. Okay, you will see, observe this very carefully. Okay, so this is called elastic after effect. Okay, and it is also called recovery. This is time dependent. Okay, you can see that it will slowly unfold itself after the initial spring back effect. Okay, so many plastics like a long chain polymer. Now, from your course in organic chemistry, I guess you should be aware of what a long chain polymer looks like. So, polyethylene, which you use, the polythene which we use for, I mean, it's now banned in many places, but we used to carry out a lot of things in that. So that is one of the examples, and you can have lots of other longer chain examples as well. So the long chain polymers is something you are aware of, and many plastics fall into that category. So they offer a mixture. These, I mean, when you do this experiment on those plastics, you may not be able to do this one. Okay, I mean, you have done it for a matchstick, you have done it for a paper clip, steel for that matter, but maybe you won't be able to do it for this one. And but this is just something which you should know, that these sort of plastics exhibit a mixture of creep. Remember what creep was? The deformation was increasing in time despite the fact that the applied force was remaining the same. And elastic after effects, which you have just read. So this and this can be seen in most of these plastics. So one of the things is this. This was what, remember, time independent, and this elastic after effect is time dependent. Okay. So this is called viscoelasticity. And what do you think a mixture of a time independent and a time dependent process is? Is it time independent or dependent? Yes, I mean the mixture will be dependent on time. So this viscoelasticity is different from plasticity in that respect. That it does not, plasticity does not depend on time, viscoelasticity does. Okay. So this word you must have heard before, visco. So it's just like viscous fluids like honey or similar sort of materials. And this is sort of the end of this discussion which we wanted to have about these type of behaviors which you would see. And what we have discussed today is the kind of materials and their behavior under a load would be, just in a very crude way. We haven't actually gone to the engineering part right now, which we will in the next class. And from there on, we will develop eventually a relationship between stress and strain. There'll be many more theory and new terms which will be coming in. So like the which I have told you about, I mean they are in italics in section 5.1, so you should see that, visualize those. Like creep is one example. Please Google or go to a video on YouTube and see how a creep experiment looks like. Okay, you should be able to see that the forces remain constant but the deformation is increasing with time. You should be able to see that. Okay, similarly you can search for all those things and get a better idea of where all these things happen. Okay, so we'll now proceed in the next class to the other topics, and lots of other definitions which all will also come. So I request you to please pay attention and note down those words and definitions and meanings exactly as they are, so that there is no confusion at your end. Okay, by the time people pass their undergraduate degree, they are always confused between what is creep, what is fatigue, what is viscoelasticity, what is plasticity. So I don't think any of that should happen with you. Okay, so we'll continue in the next class. Thank you.